in this fourth quantum mechanics lecture, we are eventually going to get on to the Schrödinger equation, which is one of these workhorses of quantum mechanics. So previously we covered a quantum state and how to build them from pure states. But what are we going to do to those states? And the Schrödinger equation tells us what we're going to do to them. But before we get on to that, we're going to get some kind of the jargon out of the way, these concepts that underpin it. So we're going to look at the idea of operators and observables and also eigenfunctions. So before proceeding on to things like equations and the Schrödinger equation, make sure you are really comfortable with those three terms right there. So let's start with observables. Well, observable is almost self-explanatory. It is a property that we can observe. It is something that we can measure, and it is quantifiable. These are things like momentum, energy, position of an object, or its spin, for instance. And when we're talking energy, this point will come into its own in the next lecture. We are really interested in the kinetic and the potential energy. These are added together to make a total energy. So when we're talking energy, we need to be quite specific about what we are talking about, which one. Now, for every observable, there is a corresponding operator. That's quite an important point to remember. But what is an operator? So, an operator, basically, it's a mathematical tool. It's a mathematical object. It is equations, it is matrices. It is something that we can apply some mathematics to. And it acts on a quantum state. So a quantum state is a mathematical function. An operator will mess around with a mathematical function. So if we treat it just like a black box, the quantum state hops into the operator and out pops a slightly modified, changed quantum state. How that works in specifics we will get on to very soon, but for now, think of it in terms of the abstract. We take a quantum state, we mess around with it, we get a new quantum state out. It is described by a mathematical function just the same. So let's look at a brief example. We're not going to cover the maths of it too much, but this is the kinetic energy operator. And we can kind of unpack a little bit about what it does. Here, it's a second derivative. So if you're used to calculus, you will be able to do that. You know what that means. Here is the reduced Planck's constant squared, and here is the mass, and it's multiplied by -1. So this is a kinetic energy operator. It allows us to get the kinetic energy of a particle. We are going to apply this later when we get to particle models. Now the next bit of jargon is the idea of an eigenfunction. If you haven't come across this word before, it's German, meaning its own function, something like that. It doesn't directly translate into English very well. But as most things, it is just a mathematical function. It has variable, we are multiplying things, adding things. It's a function. And it can be acted on by an operator. So an operator can take an eigenfunction and mess it around just a little bit. It can take a derivative, it can multiply it by something, and so on. And once it's all done with that, out pops the exact same function again. However, it will be multiplied by a constant value. So the operator changes the eigenfunction, spits back out a scaled version of that function. Not added, not shifted, not completely transformed, simply scaled. And that scaling factor, the amount that it's multiplied by, is the observable. And that is the relationship between operators and observables. We take a quantum state, operate on it, we will get the observable out if it's an eigenfunction. So let's do a bit of specifics about what an eigenfunction is and what it isn't. So let's pretend we've got this operator here. It is a capital letter, usually with a hat on it. Yes, that notation is used for basis vectors as well, but no, I don't make the rules here. And this operator is telling us to add 2 to the function. And the function, we're going to take a basic mathematical one, 4x squared plus 3x. And the operator is going to add 2 to it. So let's do it. Now, operating on that function gets us 4x squared plus 3x plus 2. Now you can see the same function in there, but that's not an eigenfunction because the whole thing is not a multiple of it. We've added 2 to it, but we can't factor the original thing out just to get a single multiple. So that is not an eigenfunction of that operator. An eigenfunction that is would be something like this. So an operator here is d by dx. We're taking a derivative. So if you've done some calculus, you'll be comfortable with that. And the function is e to the power 2x, or exponential 2x. Most eigenfunctions will be in this format because of the properties of how exponentials interact with derivatives. So let's do it. Let's see what the result is. So in this case, we take the derivative of e to the 2x, we get 2e to the 2x. Really straightforward, this one, because whenever you take a derivative of an exponential, you will always get the original back. That's a property of an exponential. Its rate of change, its first derivative, is always proportional to its value. So these will always happen with exponentials when you take a derivative. And we also have a constant function here, or a constant value, multiplying it. So this here is the eigenfunction, and this here is the eigenvalue. So this operator represented a particular observable, an energy or a position. The value of that observable would be 2. Now we're going to quickly recap before we show the Schrodinger equation to show you what the notation is. So remember, all of these symbols at the top here could mean quantum states. Sometimes we use the capital psi, sometimes we use the lowercase psi, sometimes we include the variables. So in function notation, if you're used to f of x, for instance, it's the same thing, we've just changed f for a Greek letter instead. Everything in the bracket is a variable of that function. So this one is changing along the x-axis and also with respect to time. And again, to bring that ket notation back, if you see these, they're here for completeness. We're not going to cover it too much right now, but those also mean quantum state. And things like this mean operator. So we have big H with a hat on, meaning an energy operator. We have potential energy, kinetic energy, a generic O operator, and position and momentum. These will be listed elsewhere, so you don't need to memorize them from this side, but all of those mean operator. And then this is the Schrodinger equation. Deceptively simple in this format, but you can kind of see how the eigenfunction idea is working here. Here we have an operator. Here we have a quantum state. And you can see whatever the operator is doing to that quantum state, the same thing pops out at the other end. And we get a multiplied by a particular constant value. So this is an eigenvalue here. And the Schrodinger equation specifically in this case, this is known as the Hamiltonian operator. It's a Hamiltonian energy, and E itself is energy as well. We will unpack a little bit more about this in the next lecture, but for now, you can just see it and link it to the idea of eigenfunctions. So let's recap all of this. Observables, they are values that we can measure, and every observable has an operator. So the operator is just a mathematical tool, and it acts on a quantum state. So the quantum state is represented by some maths, and the operator is some maths. They can fit together and work together quite nicely. And when the states are an eigenfunction of the operator, the result we can get from that is multiplied by the observable. We get the same function back multiplied by this value.